And so now we have the definition of the generalized eigenspaces. So for an operator T and a corresponding eigenvalue lambda, we say that V is a generalized lambda eigenvector if and only if, eigenvectors can never be the zero vector. And we have that T minus lambda I applied to V j times gives you 0 for some j. So in other words, it might not be the case that T minus lambda I kills V, but if you keep doing it, eventually it's going to get dead. So that's what we're looking at. And so then the generalized eigenspace is the collection of all these. So G lambda or G lambda of T, when you need to specify the operator, is the union of 0 and the generalized lambda eigenvectors. And then what we'll see in a moment is that this is also the null space of T minus lambda I raised to the power n. And so if you recall, the lambdath eigenspace is the null space of T minus lambda I to the n. So these generalized eigenvectors are ones where maybe T minus lambda I doesn't kill it, but when you raise it to some power, then it does kill it. And then what we saw in the previous results should lead you to believe that if you apply it n times, you're going to kill as much as you can possibly kill. And that's basically exactly the content of this little theorem we have that proves that blue equality is correct. So let T be an operator and lambda be a scalar. If n is the dimension of our vector space, then G lambda T is the null space of T minus lambda I to the n. So in some sense it's saying j equals n is enough, will always get you as far as you can go in the definition. And so for the proof, we already have one direction of the containment. So T minus lambda I to the n, this is going to be contained in G lambda, because the definition of G lambda is for some j, and so here if we just take j equal to n, in the definition, then it comes immediately. Okay, so that gives us one containment. For the other containment, let's take V to be in G lambda, and then we'll go ahead and show that it's in the null space of T minus lambda I to the n. So if it's in here, then there exists a j such that T minus lambda I to the j applied to V gives you 0. Okay, so then if we apply 8.2 and 8.4 to T minus lambda I, in place of T, then we get that V is in the null space of T minus lambda I to the n. And so then going from beginning to end, we have the containment G lambda n is contained in the null space, and that's the other containment, and so we're done.